Good morning, everybody. Morgan here. Welcome to your second week of Chemistry from Home. This lecture is coming to you from the little bedroom at my house down here in Redondo. I hope you are all doing well and holding in there. So last week we introduced the idea of pH, and at this point you should have turned in one assignment to your teacher, either myself or to the other Morgan, which was pH number 3. And if you haven't yet, still turn it in. That's not a problem. We can be very understanding with due dates right about now. You're also hopefully about halfway through the Khan Academy videos dealing with acids and bases, and I think I have a due date on those of this Thursday or Friday. I can't remember which one, but it's posted on Khan. Keep working through with that, and we're going to generate some scores for you off of the assignments there. And it's becoming more and more obvious that one of their quizzes is just not working, and that's outside our control, so don't worry about that at all. Okay, so let's go into weak acids in some detail today. We have 6 strong acids: Hickel, Hibber, and High, the friendly acid, H2SO4, HClO4, and HNO3, which are called sulfuric, perchloric, and nitric acid. So, what are the weak acids? All the others. No reason to memorize those. As long as you know the 6 strong acids, you will by default know all of the weak acids. So what are the strong bases? We typically say the metallic hydroxides. Those have to be soluble ones like, KOH and NaOH and even BaOH sub 2. This is less of an issue to know these. Now the weak bases would be the others. No need to memorize. Okay. So I want to look at some equations for some dissociations, and you've done some of this before, so I wouldn't worry about it being new to you. But let's see how the strong acid and the weak acid dissociations are different. HCl, as an example, will react with water, and it will produce H3O plus and Cl minus, or HI would react with water, and it would produce H3O plus and I minus. Now for weak acids like nitrous, HNO2, which reacts with H2O and is going to give us H3O plus and NO2 minus, or acetic, which will react with water and will give us H3O plus and C2H3O2 minus. So when you look at these, they look identical, okay? The way they dissociate is the same for both strong and weak acids when we look at it in terms of the equation. The difference comes in the size of the KEQ. For a strong acid, the KEQ is big, and for a weak acid, the KEQ is very small, something like 10 to the negative 4th, okay? Now, neither myself nor Mrs. Morgan really have made a big deal about this, but some chem teachers feel it's important to draw this one as just an arrow going forward, and then to draw these as the equilibrium sign. And I'm not so hung up on that myself. Don't lose any sleep about it, because we're implying that the K is big. It's still an equilibrium. It's just the amount that goes backwards is practically 0. Okay, so what's the difference here? Extent of dissociation. So now for strong bases typically, when they hit water, they give you Na plus and OH minus. Both of these would be aqueous, okay? And K will be big. Again, a strong electrolyte. Now for weak bases, typically we get something that looks a little bit more like this. NH3 with a plus, we picked up a hydrogen and an OH minus. Okay? And for these, the K would be small. So that last chapter coming back to haunt you. Okay, so that's pretty much the end of page 7. Pause if necessary to get stuff copied down. I'm going to go on to page number 8. Okay, so what we want to do here is look at the relationship between Ka, which would be the equilibrium constant for an acid, and Kb, which would be for a base. So for the acid, we have Ha that reacts with water. That's just our generic any acid. Gives us H3O plus and A minus, and A minus, which is a generic base, could represent anything, gives us an OH minus and an HA. Now, I want to write out a Ka here. That Ka is going to equal the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. The Kb would equal OH minus times HA divided by A minus. So if I'm going to multiply these two together, Ka times Kb equals, I have H3O plus times A minus divided by HA times, then over here I have OH minus times HA divided by A minus. And if we look at that for a second, what we're going to see is that the A minus cancels and the HA cancels. And Ka times Kb equals H3O plus times OH minus, which many of you will recall equals Kw. So Kw is also equal to Ka times Kb. Okay, that's handy to know. So, to apply these ideas to pH, what is the H3O plus concentration and pH of some 0.1 molar HCl? Well, it turns out that the 0.1 molar HCl, that's a strong acid. So, HCl plus H2O gives us H3O plus and Cl minus. And if this is 0.10 molar, these both turn into 0.10 molar. So that's the H3O plus concentration. And the pH equals the negative log of 0.10. And that equals 1.00. 2 places after the decimal for the 2 sig figs. Pretty straightforward. This is what you've been doing, except we did it in those little boxes all over our pages. Now, let's write out the same thing for acetic acid. So I have 0.10 molar acetic acid. It does not fully dissociate. It partially dissociates. Okay, I think I actually hear some people screaming in the background after seeing that right there. Something has come back to haunt you, called the ice box. Minus x plus x plus x. 0.10 minus x, x and x. So we can say that Ka equals the concentration of H3O plus times acetate ion, C2H3O2 with a minus charge, divided by C2H3O2. And in the problem, this tells us the Ka is 1.75 times 10 to the negative fifth, which is a nice small k, so we can do some approximating. X squared over 0.10 minus x is equal to 1.75 times 10 to the negative fifth. So x squared over 0.10 is approximately 1.75 times 10 to the negative fifth. So x squared equals 1.75 times 10 to the negative fifth multiplied by 0.10. And x equals 0.0013, which is equal to the H plus concentration. Okay, so the pH would equal the negative log of 0.0013, which I got a 2.89 when I did that. Okay, I should check 0.00, I'm sorry, I miswrote that. 0.0013 divided by 0.10 times 100%, and that percent ionization comes out to be quite a bit less than 5%. So I'm okay with that. All right, so this is a combination of two topics, the last chapter and this chapter, and it's something that I think is going to take us some time to get used to. So I'm going to give an assignment today, which is the weak acid practice problems and questions 1 through 5 only. Now, I realize some of you have some other stuff that you might still be getting caught up on, and I just want to say that's all right, okay? There are no chiseled in stone due dates right now, okay? We want you just to keep plugging through as best you can, and if you're having troubles with some specific topic, I'd like some people to put comments into the honors chemistry group on Schoology. Don't post them just to an individual class, post it in the group, and we will be able to go back and deal with it. This is pretty much our topic for the week, okay? So we're going to spend a lot of time on it. We're going to let you get comfortable with it. We've got one lab. Yes, I actually said the word lab. What we're going to do is we're going to give you the data points and have you work through it, and it involves doing all of this. Okay, so that's your video for today. I will have all of the schedules and stuff posted by the end of the day today. The reason it's not up, to be very blunt with you, is we're having a faculty meeting at 1 o'clock today, and I want to see what the principal has to say to us before I commit to anything for the rest of the week. All right, hang in there. Have yourselves a good day. Reach out to either of the Morgans if you need to. You can contact us via Schoology or via our LAUSD email addresses. And remember that we are here for you. All right, this is Morgan signing off.